Hi, this is Fluid Statics by Zari Campos, Natalia Munoz, and Genaro Alvarez. What is fluid statics? The study of fluids at rest focuses on how pressure is distributed in a stationary fluid and how fluids exert forces on surfaces and objects. Excuse me. For a better understanding, it just means that how fluids behave when they are not moving, allowing us to predict pressure distributions, buoyancy forces, and the behavior of objects within the fluids. Other examples of this would probably be in our daily lives, maybe a tea kettle, the face of a dam, maybe the drum of a steam boiler, such things as that. Another thing as well that we'll be focusing on this presentation is our key concepts, which is going to be our four topics, which is hydrostatic pressure, buoyancy, Pascal laws, and static pressure. Examples of this, physics terms wise, it will be submerged objects, hydraulic systems, and the pressure at depths. As well as here are other units of equations of units of forces that we'll be using in this presentation as well. It is the normal force exerted per unit area. It is denoted by P, which is given by P is force over area, which equals F over A, which is a key unit of measure and a key equation that we will be using a lot in this presentation. As well as it gives you how we write Pascal, what we write as PSI, and etc. And I will be talking about the properties of fluids. Fluids, substance, the flow include liquids and gases. Another thing it is really important in this presentation is density, which is P equals mass over volume, which is an equation that you would have to remember as well, which is very important in this topic. As well as pressure, which is P, which is of course force per unit area, which we went over, which is P over F over A, which is force over area. Moving on to the next slide. Of course, I'm going to be talking about density right here. Density tells us how much stuff or mass is packed into a certain amount of space. We use density to compare how heavy something is for its size. An example of density is how a rock is heavier than a sponge of the same size, but the rock has more mass packed into it. It has a higher density, of course. The formula for density is density equals mass over volume, just how I explained over here. Over here, right here. But just as a recap, I also have some problems for you guys that we will be solving together about density problems. Our first problem is gold is sold by the troy ounce 31.103 grams. What is the volume of one troy ounce of pure gold? And then our second problem would be a trash compactor can reduce the volume of its contents of 0.350 their original value, neglecting the mass of air expelled by the what factor is the density of rubbish increased. Now, going back to our first problem, we are going to solve it. So going on to this next slide, I have both answers right here, but I have both steps as well. We're going to be focusing on this one for our given, which is the mass, which is 1 troy ounce equals 31.103 grams. And for our density, it's going to be 19.3 grams over centimeters to the third, which is our standard value of gold. And we're going to be solving for volume. So our volume is going to be mass over density, which is, so for our equation, we're going to do volume equals mass over density. So our mass is going to be 31.103 grams, and it's going to be over 19.3 grams over centimeters to the third. And that's basically all you have to do for this equation. It's a simple equation which will give us a 1.611 centimeters to the third. And right here, I even wrote down right here, volume of 1 troy ounce of gold is 1.611 centimeters to the third. This gives us the answer for problem number 1 right here, because we already have our mass. This is the given mass right here, and we have to, this is the volume that we have to find right here. Okay? Now, going on to our second equation, which is the trash compactor, going back to this, you will see we have P equals density, M equals mass, and V equals volume. The initial density of And here we're going to be talking about initial density and as well as final density, which is why we have the PI, which is initial, and PF, which is final. It's going to be, and here's an equation that you'll see: PI equals MI, which is VI, which is initial mass and initial volume. As well as over here, I wrote it down also: PF equals MF, which is VF, which is final mass for final volume. Sorry. So our given right here is our final volume, which is 0.350, and we're trying to find the initial volume, which is right here. Why I wrote VF, which is final volume, equals 0.350 times VI, which is initial volume. We don't know our initial volume, so we put VI over 0.350 times VI equals 1 over 0.350, which equals 10.350. And I stopped there just because, granted, you could keep going, but once you find, we're not trying to find our volume. We're just trying to find our density, our final density, or our initial density, excuse me, because we already have our final. And so right now we have PF and then over PI, which equals 1 over 0.35F, 0.350, which equals 2.857, which equals 2.86, which means our density increased to 2.86, which is our, as you can go back here, which is the density of that our rubs increased by the factor right here of its original value. And then moving on to that, after that, we're going to go to the pressure. Here we're talking about how pressure increases due to the weight of the fluid above, and we also break down our equations, or what is in our equation, which is going to be a hydrostatic pressure equation, which is P equals P0 plus PGF, which is P equals pressure at depth, which is right here. PO, where P0, is equal pressure at the surface, which is right here. H equals the depth in the fluid, which is right here. And of course, G equals gravity acceleration due to, of course, gravity, which is 9.81. And right here, we're going to do some problems. So it's going to be pressure problems. Right here is the pressure, is the amount of force pushed into a certain area. The deeper you go into the fluid, the more pressure you feel, because there's more fluid above you pushing down. We're measuring pressure using units like Pascal's PA, and the formula is pressure equals force over area, which is an important equation, like how I said, that you guys need to know. And ignore the answer right here, sorry, but right here I have, as a woman walks, her entire weight is momentarily placed on one heel on her high-heeled shoes. Calculate the pressure exerted on the floor by the heel is if it has an area of 1.50. The woman's mass is 55 kg, and then you express the pressure in PA. So right here, of course, you see the answer. Sorry, but it's going to be 3.59 times 10 to the 6 PA. But right here, you have P equals force over area, which is going to equal mass times gravity over area, which you have right here, which is 55 kg, the mass of the woman. Gravity right here, which is 9.8 as always remember that. Area, which is the area of the heel, as you can see right here. And then we're going to do multiplying by 1 meter over 100 centimeters, because of 1 PA equals 1 N over meters squared, which is going to be right here. I couldn't write it, but it's going to be right there. I don't know if you see it. This little area right here. I just wrote it in. After solving that, your answer, you're going to end up getting 3.59 times 10 to the 6, which is PA. Always remember to write down your givens. Right here, your given is the mass of the woman, which is right here. And then the area, which is the 1.5. And as always, gravity is always a given, which is going to be 9.8. Always remember that to make it easier on you guys yourself whenever solving something like this. Going on to the next slide. It's going to be Pascal's law. A change in pressure applied to an enclosed fluid and transmitted undiminished to all proportions of the fluid and to the walls of its container. This is an important concept to remember when dealing with fluid statics. It's an important law that takes place in all the equations, not all equations, and certain topics of fluid statics, as well as Archimedes' principles, which is the body submerged in the fluid experience of buoyant forces equal to the weight of the fluid it displaces, which is something to always remember, which is going to come into and a lot of equations and in handy if you remember this kind of stuff. As well as right here, common fluid static problems, pressure differences in kinetic vessels, buoyancy problems, floating or sinking objects, hydraulic systems and force manipulations, multiplication, which is right here, the problems. You'll see right here, buoyancy forces. It's one of the problems that you'll see, as well as others throughout the PowerPoint that I have gone over, such as pressure differentials, and of course the force multiplications with the hydraulic systems. I found it that we should give you guys an equation. Maybe you guys could give it to your professors or anybody that you guys want to test out and that says that they know physics or fluid statics, and so you guys could give it a try as well, so you guys could practice as well. Here's the equation. It's going to be a 2.50 kg steel gasoline can hold 20.L of gasoline when full. What is the average density of the full gas can, taking into account the volume occupied by the steel as well as by the gasoline? Here's a problem for our audience, which is you guys, that we thought we could send you guys home with, just so you guys could practice as well as have a better understanding of what fluid statics is once you give it a try on your own. And here's the summary of what we hoped that we covered in this presentation in PowerPoint. We hope that we covered the fluids exert pressure due to the weights. The pressure increases with depth. Pascal's and Archimedes principles are foundational of fluid statics, and fluid statics is essential in many engineering and natural systems. We hope that you guys learn something, have a better understanding of fluid statics, and as well as I hope that you guys have a better understanding of the equations or just certain things that maybe it wasn't clear to you at the beginning of our presentation, and that now towards the end that you guys have a better understanding, a better grasp at it, or maybe just a better understanding of how you use certain equations for certain scenarios. Such as, I want you guys as well to find out, after solving this, where does this go? How does this tie to either buoyancy problems or pressure differentials or hydraulic systems? I want you guys to also write that down to see maybe if you guys can figure that out as well, or even to Pascal laws or anything like that. So this way you guys can have a better understanding of maybe of fluid statics, and as well as maybe just the physics and overall. Just once, because once you start doing this and you start making connections like that throughout physics, it's going to be a whole lot easier for you guys, and hopefully that you guys have a blessed year and everything. This is the end of our presentation, and I hope that you guys enjoyed it.